Today we're going to talk about morphism, polygons, and convexity. Yesterday we discovered that there were 6 symmetries for equilateral triangles shown in the figure. So I have the identity mapping, reflection over L, reflection over M, reflection over N, the rotation with center X, 120 degrees, going counterclockwise, positive, and the rotation around X going 120 degrees clockwise, negative rotation. So another way we can represent this is by saying where my vertices get mapped under each rotation. So you'll notice if I call row 1 my 120 degree counterclockwise rotation, A would go to B. You can see A. Here's my center X. It goes 120 degrees in a counterclockwise fashion. A goes to B, B goes to C, and C goes to A. If I want to talk about where the vertices go under a line reflection, such as reflection over line M, B goes to B, but A goes to C, and C goes to A. So we can define all of these mappings by talking about where the vertices go. And we can compose mappings together. So for example, if I first reflect over line M and then I rotate, A would go to C and then C would go to A. So the composition sends vertex A to vertex A. Then B would go to B and then B would go to C. So this is my result here. And then finally, if C gets mapped to A would get mapped to B. So overall, C would end up at B. Well, if you compare this mapping, you should see that this composition is the same as if I had just reflected over line L. So when we compose two of these together, we can get a mapping that may be achieved in a totally different way. Here you can see the operation table with composition, where I have the set of all my equilateral triangle symmetries composed together. So if I compose the identity mapping with any of these, I just get back exactly what I started with. So the first row is repeated here, the first column is repeated here. But if I compose a 120 degree rotation in a positive clockwise manner, and then I do it again, what I end up with is a 120 degrees clockwise rotation. So this table summarizes all the results of my compositions. Here's an operation table that you saw in algebra, groups, rings, and fields. Does this table look familiar? It should. It looks very similar to the last table where I let H equal this transformation and so on. If I let H, I, J, K, L, and M be equal to all the mappings on the previous page, you can see that everything lines up exactly the same way. Relationships such as this have special types of names. So I'm going to talk about a couple different kinds of what we call morphisms so that we'll be able to describe relationships like we saw in the last example. So the first type of morphism is called a homomorphism, and it's defined over here on the left. I have two operational systems. Then F, a mapping, is a homomorphism from H star to K diamond, denoted this way. If and only if F takes H to K, and for all A and B in H, this relationship holds true. Now, I wanted to show you an example of something that was homomorphic. So here, I'm going to let H star and K diamond be these. I'm going to let the set of all integers with addition be H comma star, and the set of all G, the set 1, -1, I, and -I be K, and multiplication be diamond. My function, I'm going to let equal I to the power X, where X is an integer. So my function is a homomorphism from from integers with addition to my set G with multiplication. And I'm going to show that that's the case. That means for all A and B that are in Z, just like over here, A and B are in H here is Z. For all A and B in Z, f of A plus B plus is the star, and that has to equal f of A times f of B. Times is the diamond, like it is here. So let me show you how this works. If I picked two numbers, A2 and B3, and plugged into this, you would see that it would always hold true. So f of 2 plus 3 must equal f of 2 times f of 3 in order for this to be homomorphic. So that becomes f of 5. Well, f of 5 is just I to the 5th, f of 2 is I squared, and f of 3 is I cubed. Well, you'll notice due to exponent rules, when you multiply, this is I to the 5th. So exponent rules say to add. Clearly, I have an imaginary number here, and these numbers that I'm choosing, 2 and 3, get added before it's put on the exponent. So this will always be true, and this is an example of a function that's homomorphic. Another type of morphism is called isomorphism, and in isomorphism, F is an isomorphism from H to K, denoted F, H comma star, and then the ISO over the arrow, K comma diamond, if and only if F takes H to K, and it's a one-to-one and on-to relationship, and F from H to K is homomorphic. Now, our previous example was not one-to-one. I had the set of integers and the set G, which contained 1, -1, I, and -I. So this was not one-to-one because if f of x is equal to I to the x, f of 2 is equal to I squared, which is -1, but also f of 6 is equal to I to the 6, which is I to the 4th, times I squared, and I to the 4th is 1, so this becomes -1. So 2 goes to -1, and 6 goes to -1, and therefore it is not one-to-one. So our previous example was not an isomorphism. But I have now defined two different functions and two different sets that does display isomorphism. So my first set is my integers mod 3, which includes 0, 1, and 2, with mod 3 addition. And this is the table that results. Then my second set is the set containing A, B, and C, and I've defined upside down triangle in this table. So if I did A, upside down triangle A, I got back A, and so forth. Now, the mapping F of Z3 onto G is an isomorphism. I've let F of 0 be A, F of 1 be B, and F of 2 be C. So first you should notice that my function F is one-to-one. 0 gets mapped to A, 1 gets mapped to B, 2 gets mapped to C. I do not have two arrows going into the same location. So the first requirement is met. It is one-to-one. It is also onto. Every element of G has an arrow going in. So the next thing I need to consider is whether or not homomorphic as well. So I need to check. I need to show that if I do mod 3 addition on two numbers inside my function, it's equal to the function of each of those numbers upside down triangle. So you can see here that f of 1 plus 2 in mod 3 addition is 0. Now, f of 1 and f of 2, f of 1 is B, f of 2 is C, and then if I look at what f of 0 is, it's A. If I look at B upside down triangle C, it's A. And if you were to continue to look at this, you would see that it always holds true. Further, if you look at the format of the tables, you should be able to see that the format is laid out in the exact same way. So if f of 0 is A, if I replaced all these zeros with A, that's what you would see in this table. If f of 1 is B, if I replaced all my 1s with B's, that's what you would see in this table. F of 2 is C. I replace all these 2's with C's. So really, when we talk about isomorphism, what we're talking about are two operations on sets that are as the same structure. These are both structured the same way. There are several different kinds of morphisms, and those are summarized on page 65 of your book. If you're interested in reading more about them, they are there. And then there is also an additional problem that I'm going to assign as homework tonight that will allow you to show that the triangle symmetries, the composition of those, is isomorphic with another operation and set. The next item we need to discuss concerns betweenness of rays. So we're going to let X, Y, Z, and W be coplanar points, meaning they're all in the same plane, such that X, Y, and Z are not collinear. And you can see that's what I have over here. X, Y, and Z are not collinear. They don't lie on the same line. And the ray YW here is between the rays YX and YZ. Then the ray YW here must intersect the segment that connects points X and Z, but that does not include either of those endpoints. And you can see here that that would definitely be the case. Ray YW must intersect that segment. It would not intersect either X or Z. If it did, it would not be between these two rays. If you'd like to see this proven, it's on page 66 for your reference. Betweenness of points and rays. Let X, Y, Z, and W be coplanar points, just like we saw before, such that X, Y, and Z are not collinear. X, Y, Z, not collinear. Then the ray YW is between the rays YX and YZ if and only if YW intersects segment XZ. Might as well draw it. So it must intersect segment XZ at a point that is between X and Z. If that's the case, then we can say that YX is between YW and YZ. So the only thing that is different here is that it's an if and only if statement. So I can say that my ray is between these two other rays if the ray intersects the segment, and I can also go in the reverse order. If the ray intersects the segment, then the ray must be between the two. We also need to discuss points with distances from a line. So we're going to let pi be a plane and let L be a line in pi. And you can see that I have my line L drawn here. And let P be in pi be a point such that P is not on L. So we have the point here. Let K be the unique line in pi that is perpendicular to L and passes through P. So here's my line K. It's perpendicular to L, passes through P. And we're going to let Q be the point of intersection of those two lines. Then for all points X that are elements of my line but not Q, the distance between P and Q, the length of segment PQ, has to be less than the length of segment PX. And if you think about it, it makes sense. The shortest path between 2 points is the direct path, which is that perpendicular path. Well, Now, if we look at the length of PQ, it is by definition the distance from P to the line L. So this result tells us that the distance from P to L is in fact the minimum distance from P to any point of L. I would like you to do exercise 86. In this exercise, we're going to let pi be a plane and L be a line in pi, and we're going to let P be an element of the plane that is not on the line like shown here. We're going to let K be the unique line in pi that is perpendicular to L and passes through P here, and let Q be a point in the plane where L and K intersect here. Finally, let X and Y be elements of L here and here such that X is between Q and Y. So it's between Q and Y. We're going to complete this proof that shows PX, this segment, has to be shorter than PY, this segment. So press pause on your video, complete exercise 86, and when you're ready for the answer, press play again. So this is how we prove that XP is shorter than YP. So we're going to let L, P, K, Q, X, and Y be as described. Since triangle PQX is here, is a right triangle, we have by exercise 7 that the measure of angle QXP must be less than 90. Remember, both acute angles in a right triangle are smaller than the 90-degree angle. But since QXP and PXY are a linear pair, PXY and QXP are a linear pair, we know that angle PXY here has to be greater than 90 degrees. We also notice that triangle PQY here is a right triangle, and hence by exercise 7 again, we have the measure of angle QYP here is less than 90 degrees because it's an acute angle of a right triangle. But this angle measure is equal to the measure of angle XYP. XYP, they're the same angle. Taking this together with star, it follows that the measure of angle XYP is less than the measure of angle PXY. So, and that comes from this. So I know that XYP is less than 90, and I also know that PXY is greater than 90. So I get this relationship here, and therefore the measure of angle XYP is less than the measure of angle PXY, from which it follows that by A5, that the side opposite my smaller angle is smaller than the side opposite my larger angle. The angle bisector theorem says that if a point is on an angle bisector, then it must be equidistant to the sides of my angle. So we're going to let angle ABC be an angle in the plane pi, a point X be an element of pi. It's equidistant from the rays BA here and the ray BC here, if and only if X is a point of the bisector of angle ABC, such that either X is equal to B or BX is between BA and BC. So X could potentially be on B, and then of course it is the same distance from each of these rays. It's actually on those rays. It's sometimes important to be able to tell if a distance from a point to a ray exists. So in this picture, you can see the distance from R to my ray PQ would exist. But if I were to draw a point, say, over here, that distance would not exist because it would never even intersect that ray. So formally, we talk about it this way. Let pi be a plane and let P, Q, and R be elements of my plane such that P is not equal to Q here. Then the unique perpendicular to line PQ that passes through R meets PQ in a point of the ray PQ if and only if R is an element of the open half plane determined by L that contains Q union L, where L is the perpendicular to PQ that passes through P. So if you think about it, this makes sense, because if I'm looking at the half plane determined by L containing Q, the only way the distance is going to make sense from R to my ray is if somehow the line that's perpendicular to the ray intersects it. It will only happen if R is on this side of my half plane. We can tell if the midpoint of a segment is contained in a convex figure like this. We're going to let pi be a plane and G be a convex set in pi. Let A and B be elements of pi such that they're distinct points, and that AB is a subset of G. If G contains at least one point in each of the two open half planes determined by AB, and we can see here I have my segment AB. So if G contains Y and it also contains X, ones on each side of my open half planes, then the midpoint of AB here is in the interior of G. A convex triangular region is defined this way. We're going to let pi be a plane and A, B, and C be three non-collinear points in pi. Let F be the geometric figure created by the half plane determined by line BC containing A. So here is line BC. It contains A, this side of my half plane, intersected with the half plane determined by line AC containing B. So here's AC, it contains B, this direction, and the intersection of the half plane determined by AB, this side, containing C, this way, and the union of segment AB. So as I look at this triangular region, it is the interior of the triangle, but also includes each side of my triangle. Then F is a bounded convex set such that triangle ABC is a subset of F, and the boundary of F is equal to triangle ABC. Thus, triangle ABC is a convex polygon whose associated convex polygonal region is F. So, bounded polygons. Let pi be a plane, then every polygon in pi is bounded in pi. So not just triangles, but every polygon in the plane is bounded in the plane. So here is the proof of that. We're going to let pi A, B, C, and F be as described on the previous page. To help us show that F is bounded in pi, we must first prove that every polygon in pi is bounded in pi. So we're going to let G be a polygon in pi. Then G is an n-gon for some n where n is a natural number excluding 1 and 2. So I have a polygon with n sides. Thus, there is some finite set V of points in pi that comprises the vertices of G, and some set S of line segments in pi that are the sides of G. Further, the number of vertices is equal to n, which is greater than 2. Hence, there exists at least one point, say P in V. Consider the set Px, the distance from P to x, where x is a vertex that's not P itself, of all the distances from P to each of the other vertices of G. This is a non-empty finite set of positive real numbers, so it has a greatest element, say R. Now, in order to show that it's bounded, we have to find a disk that contains G. So we're going to let D be the closed disk in pi with center P and radius R. Then D is a neighborhood in pi. We show that G is a subset of D. So let L be elements of my segments. So I have L is an element of all the sides of my polygon, then L equals segment AB for some distinct A and B that are elements of all the vertices. Since R is the greatest element of my distance of P from each of the vertices, we have that PA is less than or equal to R, and PB is also less than or equal to R. Hence, A and B are elements of D. Since D is a closed disk, we know by the convex disk result that it is a convex set. Consequently, segment AB is a subset of D. That is, L is a subset of D. The same is true for every line segment in S. Hence, the union of all the segments in S is a subset of D, but the union of all the segments in S is G. Consequently, G is a subset of D. It follows that G is bounded in pi. Now I would like for you to work through the following problems: exercises 84 through 85 and 89 through 92. Have a great day.